Today, we're going to talk about network optimization, specifically finding the shortest path. In a network optimization shortest path problem, the goal is to find the shortest distance between two locations. The beginning location is called the origin node, represented here by node O, and the final location is called the destination node, represented by node D. In between these two nodes, there can be intermediate nodes that offer alternate paths. These nodes are called transshipment nodes, represented by nodes A and B. There can be multiple paths between nodes called links. Links can be followed in both directions between nodes, while a one-way link is called an arc. Arcs are always used when connecting to the origin and destination nodes. Links and arcs are assigned lengths, which are positive values that represent the distance between the two nodes the link is connecting. The objective of a shortest path problem is to minimize the total distance traveled, denoted by this equation, where I and j are the start and the end of each arc. Each arc is assigned an x value denoting whether the path is taken or not. If you take the path, x equals 1. If not, x equals 0. Each arc also has a c value, which represents the distance between two nodes. Here's the complete objective function for this example. As we explained before, the coefficients here represent the distances, and the x's are the arcs between nodes. Notice that this section, in parentheses, accounts for traveling between A and B in both directions. You can only take one path out of the origin, so our first constraint represents this concept. Either you take the path from the origin to node A, or the path from the origin to node B, but not both. So the sum of those possibilities must equal 1. The constraints for transshipment nodes are calculated by taking the outflow minus the inflow. Each of these constraints must equal 0, because everything that goes into a transshipment node must come out. Lastly, you find the destination constraint by taking the negative of the arcs leading to the destination node and setting it equal to -1. Last but definitely not least is the non-negativity constraints. These constraints make sure that all our x values are positive. You can't travel negative distance. And here you can see the shortest path mapped out, from the origin to node A to node B to the destination. Hooray! Now you might be wondering why this is at all relevant to you. As systems engineering students, we often need to travel from the far reaches of campus to our home in 1776 G Street in a short amount of time. Our problem was to create a method for determining the shortest path from these far reaches of campus to 1776 G to minimize our walking distance and maximize our efficiency. Let's take a look at a situation we can relate to. You find yourself in Tompkins and no one knows why. Now you are running late and need to get to class in 1776 G Street as soon as possible. How are you going to do it? You can see on the map, from Tompkins, we can either go to G23, which will take us 220 feet, or H23, which will take 227 feet. We use Excel to solve linear programming problems like this. Excel has a helpful tool called Solver to determine the solution on constraints and decision variables. We start our Excel solving with these two connections. The decision column is currently filled with zeros because we don't know which path we are taking just yet. The remaining links in the network shall be filled in the same fashion until it looks like this. As we saw in the introductory problem, there are flow constraints for the origin, transshipment, and destination nodes. Let's start with the origin node. We will use the Excel function SUMIF. SUMIF looks in a column for a specific node name and will then return the corresponding decision variable for that node. So we select the from column, then lock it. Then select the node name in the current row, then select the decision column and lock that. Repeat this process for the in column, but with the to column instead of the from column. The outflow minus inflow column is the difference between the outflow and inflow. Because Tompkins is the origin node, we expect the net flow to equal 1. Now let's take a look at one of the transshipment nodes, for example, G23. We use the same formulas as the previous row by clicking on the bottom right corner of the cell above and dragging it down to the current row. The net flow of a transshipment node should be equal to 0, so enter in 0 in the net flow column. Now we continue adding transshipment nodes and their links until we reach the destination node. Here's the table fully populated with transshipment nodes. Now we can enter in the destination node. We don't expect to leave 1776 G Street because that is our destination. Therefore, the net out minus in should be a -1. As we stated in the intro, we are trying to minimize the objective function, which is equal to the sum of the distances traveled. In this cell, use the cell function sum product of the decision variable column and the distance column. Once we've completed typing in our constraints, we can use Excel Solver to find the shortest path from Tompkins to 1776 G Street. Go up to the Data tab and click on Solver. Our objective is to minimize the distance, so we set our objective function equal to our minimum distance cell. Be sure to click the Min button. Next, our variable cells are the decision variables. Thus, we choose the decision variable column for this field. Finally, we click Add, and for our cell reference, we select the entire out minus in column. Set the equivalency equal to equal. Now, the constraints field becomes our entire net column. For the constraint field, select the entire net column. When finished, click OK. Select the solving method simplex LP. We are now ready to solve the objective function, so click Solve. We now see that some of the values in the decision column have become 1s. A 1 indicates that this link has been used. Let's take a look at the shortest path on the map. A similar process can be done to determine the shortest distance from the red cross vex dot to 1776 G Street. Take note that the origin node has changed from Tompkins to the vex. finally, we see George coming from the metro since he just got back from his internship. Once again, we change the origin node now to the Foggy Bottom metro stop.